Hello, I'm going to do some experiments now where I'm going to mix a couple of chemicals together and I'm going to measure the temperature change of the reaction by using a digital thermometer and we'll connect that to my laptop and measure the temperature. So a number of different experiments and I'm going to do the experiments in a polystyrene cup. The reason being that that's an insulator, so we won't lose too much heat out into the surroundings. But I'm going to just put that polystyrene cup into a glass beaker just so that there's some stability to it. Also provides a bit of insulation around the cup as well. The first experiment I'm going to do is I'm going to mix 25 centimetres cubed of hydrochloric acid with 25 centimetres cubed of sodium hydroxide. So I'll just pour the acid into the cup. So that's in there. I'm just going to pop the temperature probe into the cup and start recording. So we see that the temperature in there at the moment is 18.6 degrees C. And what I'm going to do is I'm going to add the sodium hydroxide and we'll see what happens. So pouring that in, so 25 centimetres cubed of the acid and the alkali. Give it a stir and we can see there that the temperature is increasing. And we can see that the temperature is now very slowly starting to decrease. So that reaction has finished and it will very slowly now start to drop further. So that's the first reaction. So the next experiment, I've got some sodium hydrogen carbonate, which I'm just going to pour into the beaker. So that's in there now. And just wait for that temperature to stabilize. So again, we're at about 18.5 degrees C there. And to this sodium hydrogen carbonate, which is commonly known as bicarb, so it's a common kitchen chemical, I'm going to add a couple of spatula measures of citric acid. Citric acid is the solid when it's pure, and it's often used in food. It occurs naturally in citrus fruits, and it's a key ingredient in very sour sweets. So I'm just going to put a couple of spatula measures of the citric acid into the sodium hydrogen carbonate. Just listen carefully to that, and what you'll see is that it's fizzing, it's effervescing, so producing a gas. The gas is carbon dioxide. And if I just scale the temperature axis, we can see there that the temperature in this reaction has fallen. So this is an endothermic reaction. So reactions that give out heat to the surroundings are called exothermic, and reactions that take in heat and make the surroundings get colder are called endothermic reactions. So we started off at about 18.3 degrees. We've dropped down to 16.3 degrees, so we've lost a couple of degrees in temperature. And that seems to be stabilizing there now at 16.3 degrees. So, as I said, this is an endothermic reaction. It's also the reaction that occurs if you have a bath bomb. So the bath bomb contains the sodium hydrogen carbonate and the citric acid combined together as solids. When you put them into the bath, they dissolve, and when they dissolve, they react, and they react in an endothermic manner, which means it will cool your bath down. So, top tip is if you're going to use a bath bomb, make sure your bath is a bit too hot before you put the bath bomb in. Okay, the next reaction, I've just got some water, so 25 centimetres cubed of water, and I'll just pour that into the beaker. Let the temperature probe stabilise to the temperature of the water. So that's 17.7 degrees, 17.8 degrees. So I'll just leave that for a little while just to get to a constant temperature. And what I'm going to do in a minute is I'm going to add some ammonium chloride to that water. And what will happen is the ammonium chloride will dissolve, and there's no chemical reaction other than the ammonium chloride dissolving. So I've got the water in the beaker. I'll just add some ammonium chloride. Just put some in. So I've just added a bit of this ammonium chloride into the water. Give it a stir. And you see that as that dissolves, the temperature is dropping really quite quickly. The energy of the water is being used to break apart the structure of the ammonium chloride. And we can see that that's cooled down, another endothermic process. And that's cooled down to about 10 degrees, 9.9 degrees. This is the reaction that you get in the ice packs that you use if you've got a sporting injury. So you'll know there's a bag with a load of crystals in it, and those crystals are ammonium chloride. And then inside that bag is a small pouch of water, and when you burst that little pouch of water, the crystals will start to dissolve and will take in energy and will get much colder. So that's dropped down to 9.9 degrees C. So another a dissolving reaction. Okay, so the next reaction, I've got a new polystyrene cup and some hydrochloric acid again. So I'll just pour that acid into the beaker. Start recording, so back up to 18 degrees, so it's warming up. We'll let that stabilise. So that acid is at 18.5 degrees C. And what I'm going to add to the acid is some magnesium powder. Magnesium is a reactive metal, and we'll do a displacement reaction with the hydrochloric acid. Again, we should get some effervescence, we should get some hydrogen being produced, as well as some magnesium chloride. So I've just put a spatula measure, a good spatula measure of the magnesium into the acid. You may be able to hear that, you can see the steam as it's got so hot. Let's give that a stir. Temperature shooting up. You can see that this is a really exothermic reaction, and displacement reactions do tend to be strongly exothermic. So that has got to its highest temperature and is now starting to cool down. Now, for this last experiment, I'm going to do something a little bit different. This time, I'm going to do the reaction in a glass beaker, because I want there to be a temperature change, and an exchange of temperature from the reaction. I'm going to stand that beaker on a wooden block. Onto the wooden block, I'm just going to squirt a bit of water. So that water's now just sitting on the block. And I'm going to stand the beaker on top of that water. You might be able to guess what's going to happen. Now this is an unusual reaction because this is a reaction between two different solids. And the solids that are going to react together are barium hydroxide and ammonium chloride. So I'm going to put one of these in. I'll put the barium hydroxide into the beaker. And I'm just going to stand the temperature probe in that solid and start recording temperature. Okay, so the temperature of this first solid, the barium hydroxide, is about 19.5 degrees. I'm going to add the ammonium chloride to it. So the two solids are now together in that beaker, just there. And I'm just going to stir these two to mix them and to get the two solids to contact each other. So this is unusual because it's rare that two solids actually react together. Now, as I stir it, what you'll see is the temperature is dropping quite rapidly. The other thing that's happening is that the solids, one of the products of this reaction is actually a liquid. In fact, it's also producing a gas. You'll have to take my word for this, but it's I can smell ammonia gas being given off. I'll prove that actually in a minute. But we've got down to minus 22 degrees C, so it's very, very cold indeed. What you might be able to see as I just stir it is that it now looks like a liquid in there. So we've sort of dissolved some of the products, and say we've got gas given off as well. So we got down to about minus 30 degrees C. When you think that a freezer is minus 18 degrees, no living thing can exist without insulation at temperatures below that. We've got colder than a freezer, and just touching the side of the beaker, I can just feel how cold that is. Now, remember I spilt some water onto the wooden block. Well, what I've done is I've frozen that water. So this reaction's got so cold that the water has frozen and the beaker has now stuck to this wooden block, and I can lift the whole weight of that wooden block just holding onto the beaker, and that water has completely frozen. It's really, really cold. I did say that we could test for the ammonia gas. What I'll do, just see if this works. I've got a piece of universal indicator paper. I'll just make that moist, so just add a little bit of water to it. We may not be producing too much gas anymore, but if I just hold this over the beaker, you might be able to see that the universal indicator paper has gone dark blue without touching anything there. It's just the gas coming off this reaction has caused the indicator to go dark blue. Therefore, we've produced an alkaline gas. The only alkaline gas we've made in this is ammonia. So a very, very cool, literally, reaction there where we can freeze water from this strongly endothermic reaction.